Hello friends, welcome to New Lessons. Today we will study in a different format. So we will discuss about three-phase induction motor. So for our introduction part, let me introduce with this three-phase induction motor. These are the most widely used electric motors in industry. They run at essentially at constant speed. The most important thing is they run at constant speed from no load to full load, and hence there is no such maintenance required for this. But if we want to have different speed control, so we must use the DC motors. These three-phase induction motors are simple, rushed, low price, easy to maintain, and can be manufactured with characteristics that suit most industrial requirements. So these three-phase induction motors are very important, keeping in point the industrial requirements. Like any electric motor, a three-phase induction motor has a stator, that is a stationary part, and a rotor that rotates. The stator carries a three-phase winding called the stator winding, while the rotor carries a short-circuited winding called the rotor winding. Only the stator winding is fed with the three-phase supply. The rotor winding derives its voltage and power from the external energized stator winding through electromagnetic induction. And in the previous videos of electromagnetic induction, we have discussed how this induction takes place from the stator to rotor. This induction motor may be considered to be a transformer with a rotating secondary device, and it can be described as a transformer type also. We are comparing this with transformer because in case of induction motor, the EMF is given in the stationary, and due to induction it is carried away by the rotor, that is the secondary. So there are some advantages of this. The main advantages are it is a simple and rushed construction, very tightly constructed. It is cheaper and it requires little maintenance. It has high efficiency and reasonable good power factor. This is the most important thing of three-phase induction motor. And also it has a self-starting torque. But it comes up with some disadvantages, like it always moves with a constant speed from no load to full load, and we cannot change its speed according to our requirement. So for changing the speed or having a speed control, we have to use a DC motor. Its starting torque is inferior to DC shunt motor. So now talking about its construction, a three-phase induction motor has two main parts. You can see the stator, the outer part is the stator, and the inner winding part is the rotor. So there are several measurements regarding this. The rotor is separated from the stator by a small air gap, and this air gap ranges from 0.4 mm to 4 mm depending upon the power of the motor which you require. Now let's talk about the stator. It consists of a steel frame enclosing a hollow cylinder core made up of thin laminations of silicon steel. The insulator connected to form a balanced three-phase star or delta connected. The three-phase stator winding is wound for a different number of poles as per the requirement of the speed, and greater the number of poles, lesser is the speed of the motor. So you are aware with this formula, the relation between poles and the speed. This rotating field, that is the rotor part, induces currents in the rotor by electromagnetic induction, and we get the EMF. And this EMF is used to move the motor. Now the second important part is the rotor part. This rotor is mounted on a shaft, hollow laminated core having slots on its outer periphery. It is of two types mainly, squirrel cage type and wound type. The squirrel cage type consists of a laminated cylindrical core having parallel slots on its outer periphery. One copper or aluminum bar is placed in each slot. The entire construction, bars and end rings, resembles a square cage, and hence the name. The rotor is not connected electrically to the supply, but it has current induced in it by transformer action from the stator. So we compare it with a transformer. Those induction motors which employ squirrel cage are called squirrel cage induction motor. Most of the three-phase induction motor called squirrel cage, as it has a remarkably simple and robust construction and can operate in most of the adverse circumstances. However, it has some disadvantages like low starting torque, because the rotor bars are permanently short-circuited and not possible to add any external resistance which are used for giving a higher starting torque. In this case, the external resistance are permanently short-circuited, so we cannot apply any other resistance to make the starting torque little bit higher. Even though There are many advantages, and hence these are used widely in industrial levels. You can see these diagrams. These are a type of squirrel cage rotors. Here you can see the slip rings. Now the second type is the wound rotor. It consists of a laminated cylindrical core and carries a three-phase winding similar to that of the stator. The rotor winding is uniformly disturbed in the slots and is usually star connected. These are the windings of the rotor part. This is a kind of rotor winding. All the three parts are connected to the slip rings and hence they are connected to a rheostat. So at the starting, external resistances are included in the rotor to give a higher starting torque. Wound rotor type has a large starting torque. These resistances are generally reduced to zero as the motor runs up to speed. Now can you tell why these resistances are used? These are used only during the starting period to give a large starting torque, but when it starts, then the resistances are gradually reduced to zero. So when the motor attains normal speed, the three brushes are short circuited so that the wound rotor acts like a squirrel cage rotor, and finally it moves with a constant speed. Now the main principle behind it is the rotating magnetic field due to the three-phase current. When the three-phase winding is energized by three-phase supply, a rotating magnetic field is produced. This field is such that its poles do not remain in a fixed position on the stator but go on shifting their positions around the stator. They are moving with a phase difference of 120 degree each. Now consider the fluxes. In this case, phi x equals to phi m sin omega t. In case of y, it is separated by 120 degree, and in case of z, it also separated by 240 degree. So there is a phase shift of 120 difference within this x, y and z. These are the three phases, and phi m is the maximum flux due to any phase. So there are several diagrams explaining about how this rotor moves and works. I will enclose this PDF along with this video so you can get a better analysis, you can study it more. Now if you see, the current in the phase X is 0 and the current in the phase Y and Z are equal and opposite. Now the currents are flowing outward in the top conductors and inward in the bottom conductors. This establishes a resultant flux towards right. You can see this resultant flux. The magnitude of this resultant flux is constant and equals to 1.5 of the maximum flux, that is phi m. So there is a numerical mathematical proof regarding this. At any instant 1, say omega t equal to 0, the three fluxes are given as one of the fluxes is at 0, that is phi x is 0, phi y equals to phi m sin minus 120 degree, which is equals to root 3 by 2 phi m, and similarly phi z equals to root 3 by 2 phi m. So the phasor sum of minus phi y and phi z is a resultant of phi r, and the resultant flux is given as phi r equals to 2 root 3 by 2 phi m cos 60 by 2, and hence the output is the resultant flux comes up to be 1.5 phi m, as said before. Similarly, at instant 2, if we consider phi y is 0, you say phi y is maximum, you can say, at 30 degree, and hence if you solve it, you will get the same thing. You will note that the resultant flux is displaced by 30 degree clockwise from the position 1. And similarly at instant 3, suppose the current is in phase Z is 0 and the current in the phase X and Y are equal. In this case also, at omega t equals to 60 degree, if we draw the fluxes and calculate them, we'll get these values. Here phi Z is 0, and by solving numerically you will get the same resultant flux, that is 1.5 phi m. So in this way we can get the maximum flux at several positions. The next topic is the speed of the rotating magnetic field. The speed at which the rotating magnetic field revolves is called the synchronous speed. You are aware of this term, that is synchronous speed. Now if you refer to the time instant before, during 1 quarter cycle the field has rotated around through 90 degree. We are discussing about 1 quarter cycle, so the field has rotated through 90 degree at a time instant represented by 13 or 1 completed cycle of current Ix from the origin. The field has completed 1 revolution. Now here P is the number of poles. The rotating field makes 1 revolutions in P by 2 cycles of the current. So the cycles of the current is equals to P by 2, means half of the poles into revolutions of the field. Number of poles you can say in the half revolution of the field, and per second if you want to calculate, it is P by 2 into revolutions of the field per second. So we get this formula, Ns equals to 120 F by P. This is a very well known formula, we have studied previously also. This synchronous speed is equals to 120 into frequency supplied frequency by the number of poles. So the speed of the rotating magnetic field is same as the speed of the alternator that is supplying power to the motor if the two have the same number of poles. Hence the magnetic flux is said to rotate at a synchronous speed. So this is a type of synchronous speed in which the induction motor moves. Now there is the direction of rotating field. There are several theories regarding this direction of rotating field. You can get it. This can be reversed. The direction can be reversed by interchanging the two or more supply lines. Now there is a mathematical proof showing the rotating magnetic field. You can consider this figure. The three phases are at a distance separated by 120 degree. All the three phases are marked with phi 1, phi 2, phi 3, which is magnitude. Now the three phases having the produces fluxes phi 1, phi 2, phi 3, which vary sinusoidally. To find the magnitude of the resultant flux, we have to resolve each flux horizontally and vertical components and then find the vector sum. So by doing that, you can go through this you can go through this numerical part. All the components has been resolved into horizontal and vector components, and the vector sum has been calculated. So the final resultant value is the flux of horizontal and vertical part. It comes up to be 1.55 m, which is constant. That is the maximum value of flux, resultant flux, and does not change with time. Most important thing, it does not change with time. Thus the resultant magnetic field rotates at constant angular velocity of omega equals to 2 pi f. For p poles machine, means having number of poles p, omega is given as 2 omega by p, and hence again you get the synchronous speed as 120 f by p. For example, here you can see the example. I will enclose this PDF, you can study it well. For a 6-pole 50 Hz 3-phase induction motor, N equals to how much, can you guess? It's simple, 120 into the frequency, that is the 50 Hz, by number of poles attached, that is 6. It comes up to be 1000 rpm. It means the flux rotates around the stator at a speed of 1000 rpm. So in this way you can calculate 2-3 numericals regarding this. Next, coming to the principle of operation. Consider 3-phase induction motor. The operation of this motor can be explained as we are going to discuss like this. In the diagram you can see the rotation of stator field, the air gap between the stator and the rotor, which is around 0.4 mm to 4 mm. These are the rotor conductors. When a 3-phase stator winding is energized, you can see how this 3-phase stator winding are energized. From a 3-phase supply, a rotating magnetic field is set up which rotates the stator at a synchronous speed, and this synchronous speed is given by 120 f by p. The rotating field passes through the air gap and cuts the rotor conductors, and this is what happens in electromagnetic induction. Due to the relative speed between the rotor flux and the stationary rotor, EMF are induced in the rotor conductors since the rotor circuit is short circuited, and hence we get the EMF. We get a motion. The current carrying rotors conductors are placed in a magnetic field by the stator produced by the stator, and a mechanical force acts on the rotor conductors. The sum of the mechanical force on all the rotor conductors produces a torque, and this torque tends to move the rotor in the same direction of the rotating field. The fact that the rotor is urged to follow the stator field, the rotor moves in the direction of the stator field, and the reason for this is the Lenz's law. It will oppose the cause that produces it. So it moves along with the stator field, and hence we get a unidirectional movement of the rotor. So this is the basic principle of rotation of induction motor. Now coming to a very popular topic, that is the slip of the induction motor. Now the speed of the rotor can never reach the speed of the stator flux, because the stator flux gets the three-phase supply, makes a magnetic field, and that magnetic field is cut by the rotor conductors, and hence the rotor feels a mechanical force and it moves. But even though there is a electromagnetic induction, there are some losses, and the rotor can never reach the speed of the stator flux. So there would be no relative speed between the rotor conductors and the stator field. The friction and windage would immediately cause the rotor to slow down. Hence the rotor speed is always less than the synchronous speed. So this difference in speed depends upon the rotor or load on the motor. The difference between this synchronous speed ns of the rotating stator field and the actual rotor speed n is called the slip. The slip is given as ns minus n by ns into 100. Now the numerator part, that is ns minus n, is known as the slip speed. When the rotor is stationary, that is n equals to 0, slip is 1, that is equals to 100% slip. In an induction motor, the change in slip from no load to full load is hardly changes from 0.1 to 3%, so it is essentially a constant speed motor. Now the next part is about rotor current frequency. The frequency of a voltage or current induced due to the relative speed between a winding and a magnetic field is given as this frequency, which I have learned before, is given as number n into p, that is the synchronous speed or the relative speed between the magnetic field and the winding, into number of poles by 120 degree. So the rotor current frequency is given as the rotor speed, the relative speed between the flux and the rotor is ns minus n. You know this in the slip part we have read. There is always the relative speed between the rotating flux and the rotor. So there is a difference, ns minus n, and hence we get a rotor current frequency, that is f dash. This f dash is equals to ns minus n into p by 120. So this ns minus n can be written as s into ns p by 120, or the frequency we can say is slip times the normal frequency. The rotor current frequency means the current which is flowing through the rotor, and it has a frequency that is equals to the slip into the supply frequency. When the rotor is at standstill or stationary, s equals to 1, so the rotor current frequency is same as the supply frequency. But when it starts to move, we can get a slip on basis on the formula of ns minus n by ns, and that will give the rotor current frequency is equals to slip times the supply frequency. Now the effect of slip on the rotor circuit, here is a numerical. Consider 6-pole 3-phase 50 Hz induction motor. So the ns will be 120 into f by p, it comes out to be 1000 rpm. At standstill, the relative speed between the stator flux and the rotor is 1000 rpm, and rotor EMF is E2. It is given as E2. If the full load speed of the motor is 960, so what is the speed? What is the slip? It is given the synchronous speed as 1000 and the full load slip is 960, so we can calculate the slip as ns minus n by ns. It comes up to be 0.04. Now the relative speed between the stator flux and the rotor is now only 40 rpm. So if we calculate the rotor EMF per phase, so we'll get it as E2 into 40 by 1000, that is equals to 0.04 of E2, or you can directly write it as the rotor EMF per phase is slip times E2. Here you can see it is S times of E2. This is the relative speed between the stator and rotor flux is decreased to 40 rpm, and hence the rotor EMF is reduced to S times of E2. Similarly, in the rotor frequency, you can get S times of frequency, also reduced to the same ratio, you can see. Now the per phase rotor reactance, this is also same, x2 into 40 by 1000, that is the decrease 1000, from 1000 it has decreased to 960, that is decrease is 40 by net synchronous 1000, so it comes out to be slip times of reactance. Thus, as a point of conclusion, we can conclude that the rotor EMF per phase at any slip S is given as S times of E2, rotor reaction per phase is given as S time of X2, and rotor frequency is given as SF, where E2, X2 and F are corresponding values at standstill condition. Now at standstill condition, how we will calculate the rotor speed? This is a 3-phase supply given to the induction motor, and at standstill condition the rotor current per phase, you know, I2 is given as net EMF by net impedance, which comes up to be E2 by R2 square plus X2 square. The rotor power factor we can calculate as net resistance by impedance equals to R2 by R2 square plus X2 square. These are some formulas required for numerical part. Now this was those were the conditions at standstill, that is when S equals to 1. Now when it is running at a slip of S, that means there is a difference between the stator rotating field and the movement of the rotor, speed of the rotor, you can better tell it. So the rotor current comes up to be I2 dash equals to S into E2 by Z dash 2. So it comes up to be S into E2 by R2 square plus SX2 square. So the rotor power factor is cos phi equals to R2 by Z2, and hence all the parameters will change according to it. When you consider the slip, these parameters are changing. You can see the net voltage is changing as per the previous example. In this case also the net reactance is changing as per the previous example. Now next, coming to the rotor torque. The rotor moves with a torque, and this torque is developed in the rotor is directly proportional to the rotor current, the EMF and the power factor. So this torque is given as E2I2 cos phi 2, or we can say T equals to K, that is a constant, into E2I2 into cos phi 2, where I2 is the rotor current at standstill, E2 is the rotor EMF at standstill, and cos phi 2 is the rotor power factor at standstill. The values of the rotor EMF, rotor current and power factor are taken at given conditions. Now this is a very important thing, that is the starting torque. These three terms are well known to you. We have read it previously, X2, E2 and R2. So we can express them as rotor impedance per phase, that is Z2. Now we are considering everything at standstill condition, that is starting torque. When the starting torque is given, we consider it as standstill. This rotor impedance per phase is given as Z2 equals to R2 square plus X2 square, and rotor current per phase is given as I2 equals to I2 E2 by Z2, and here Z2 can be written as R2 square plus X2 square. Similarly we get the power factor. Before we have read the starting torque, the formula for starting torque, that is K times E2I2 cos phi 2. This starting torque depends upon all the three factors, that is the rotor EMF, rotor current and the power factor. So we multiply all these three terms and the starting torque comes up to be K E2 square R2 by R2 square plus X2 square. Generally the stator supply voltage V is constant, so the flux per pole phi set up by the stator is also fixed. So in this case, keeping the flux at that constant, it means that the EMF E2 induced in the rotor will be constant every time. So we are taking this E2 as constant and hence we are calculating TS, that is the starting torque, equals to K1 R2 by Z2 square. This is the most generalized form we can use. Now it is clear that the magnitude of the starting torque would depend upon the relative values of R2 and X2, that is the rotor resistance phase at standstill, the rotor reactance phase per phase. From this formula we can say the starting torque depends upon the relative values of R2 and X2. It can also be shown that K equals to 3 by 2 pi ns, and this starting torque can be 3 by 2 pi ns into E2 square R2 by R2 square plus X2 square. You can refer the books for this derivation if you want. These are the basis of the numerical purpose. Now is one more important thing, that is the condition for maximum starting torque. So for calculating any maximum value, we have to differentiate it. So differentiating it with R2 and equating it to 0, we get R2 equals to X2. That is, when the resistance R2 is equals to X2, the starting torque will be maximum. That is the case we can better say as the rotor resistance per phase equals to standstill rotor reactance per phase. Under condition of maximum torque, the power factor is, or phi you can say, is 45 degree and the power factor is 0.707 lagging. So this was all about induction motor, its principle, about the slip, starting torque, how the maximum starting torque we can get. In the next video we will study some more thing about induction motor. Thank you.